Tudo bem, tudo bem. Um ano já, né?
É verdade, mas parece que foi muito
Oh, muito rápido.
Nós andamos para aí, já andamos para aí.
É, já está tudo conhecido. É, exatamente. Eu queria dar uma navegada. Ah, a apresentadora Ingrid, ela ficou aqui no meio, né? Passando os slides com a mão mesmo, foi? Ela vem para sair mesmo. Não, não tem problema não. Vem aqui e dou uma clicada também. Se tivesse era prático, mas se não tem um aqui já, não tem problema. Porque se tiver fácil, melhor ainda.
Não temos.
No problem, sem problema.
Acho que vamos tirar ao longo desta semana, só depois não temos.
Uhum. Deixa eu ver aqui. Can you guys back there read anything here? It's too small, the phone. It's too small, right? What about now? Yeah. We'll cut a bit the code, but I think it's enough. Let's see how it goes here, just to see. Yeah, do it too. You mean like, you mean split the terminal?
No, instead of having the default black background, with white background and black text.
Oh, that would be.
No, I tried here. If there is a theme that we can easily, maybe worth trying.
I understand. The theme would be the clean theme, the white theme.
It would be the daylight.
Yeah, let me try to do this here. Let's see.
Also, I just added on the Slack channel the link to the Zoom screen sharing. So if you don't see in the back, you can.
Oh, perfect.
Yes.
So if you go to the computer, you go Slack channel, there you want to
The mail that you just sent our sent.
Let's see if this one high contrast. Does it get better? Let's see here. Color theme. What's a good color theme? Maybe Monokai? Is it helping, like changing the theme like this? Is it better to read now with this theme? Like I would change here and you can say what's the best one. Like I have a few options here. Dark, I don't know, maybe solarized light. Plus? Light plus. It's better? Or it's the contrast is not okay? Yeah. What about this one? Yeah. Yeah, that's the zoom I think we can get because it's so small, the screen. If you increase more, there's no space for. Let's see if there's any other light modern. Maybe there's one here, high contrast, right? Like see theme. High contrast. Dark, light, high contrast. Wow. I think the dark one. So do you guys prefer dark or white? If you prefer dark, please raise your hand. And white? Okay, so maybe it's hard. Like, I'll go for dark because I think I saw one more hand. It's like, it's pretty much the same number of votes, so. Dark, high contrast. Okay. Can start?
Okay, hello everyone. Hello again to those who are attending online. So we are starting this afternoon with the presentation of Julie Woffeman called geotables.gl, a universal representation of geospatial data. Thank you.
Thank you, Virginia. So, hi everyone, welcome after lunch, right? So I'll try to do the same as Ingrid here. I'll be walking around. I think it's better and more interactive. I will be just coming back to move forward the slides because we don't have a pointer, right? But what's this presentation about here? What the goal of this talk is, I want to introduce to some of you who never seen Julia before, very basics of how do you load with one particular ecosystem geospatial data and how do you manage and process and visualize this kind of data sets, right? The idea here is that you want to merge different representations that you're probably used to from Python, R, which are, maybe you've heard the names like vector data, raster data, mesh data, all these different data sets, they will be loaded in the same representation that you'll be able to then process and visualize with easy, few lines of code. So this is what we call the geotables.gl. But let's go step by step building the motivation for this, right? So what is the motivation behind this work, this package? Geospatial data is everywhere. We know how many different formats are out there for you that are used to this, GeoJSON, shapefiles, TIFF, all kinds of different file formats, and it's always a lot of time you spend doing loading and saving of this, restructuring your code to support different formats, changing data structure to just get your job done, right? So it's a lot of time we waste, or spend, at least, doing I/O, which is input-output of geospatial data. And it's usually like very painful, right? Like the scientific questions are not about how you load the data, it's basically much more high level. And so the main motivation we had was basically, we're seeing that we've been wasting so much time rewriting code to support different formats, right? So you have different formats, vector, raster data, you have a separate script or a separate function to do this. And it's always like a lot of time wasted or spent trying to support these different representations. So how much time do you actually think is used with loading and saving geospatial data in your workflow today? Do you think it's like 50% of your time, 80% more? How much time do you think it's like loading or saving data? Any guess? Yeah. When it's done, right? So say you have a script that works with raster data, for those of you who know, right? How much time do you think you waste rewriting the script to support vector data or to support any other geospatial data representation? Is it something that you can do quickly? No. Right? It's so painful, right? So that's one of the things that we really want to try to address here. So imagine if you could instead like load raster, vector, mesh data, any complex 3D data set from dynamical systems, from PDE solving. So you have climatology, climate models, geophysics models. These are complicated 3D models, for example, of unstructured meshes. You have these solvers that are running, generating these results on geospatial data structures. And imagine that you could load every single data set with a single command line, right? So that's the idea here. Also imagine that you could visualize all these things with the same command, right? So usually when you start working with data like this, you have to have a function to load the specific format, you have a function to visualize that specific structure, and you have to duplicate your code or like many branches to handle these things, right? So what if you could do these things with the same function, right? So we saw this need, right, like for universal representation. I think many people have seen this before, so we just put the energy and work on that direction, which is a need for a universal representation. Of course, there is one thing that I would like to point out in this slide. There's the fallacy. I like it. I call it the fallacy because you see a lot of people saying, like, no single representation meets all requirements, right? And that's true, but in practice, a good representation can meet 99% of your requirements, right? So if you're working with a representation that really was designed for say, PDE solving, so you have fast access in a given dimension of your data set. So you have an array, and your array has like a dimension that's tiling together, for example, the dimension of coordinates, the dimension of samples, the dimension of time. Sometimes you restructure your data so that it has better locality for fast access, but that's an intermediate representation that's used internally in your code, right? So if we could manage to actually have a layer of abstraction that's universal, you could interact with different ecosystems, and when the time comes, you can convert to your intermediate representation internally, do your PDE solving, do your work, and come back and output the same representation. That will increase, for example, the interoperability between different ecosystems, and people can work with different ecosystems more easily. So in order to get to a good representation, we need a good definition, right? So I think in order to get to this point of actually finding out what's the appropriate data structure, we need to ask the question, what is geospatial data? And I will ask this one for you too. So what do you think is geospatial data?
Just whenever you... Because of people online.
Sorry. So what do you think is geospatial data? If you had to just give a definition now, anyone can just say a few words, like what is geospatial data for you? Is it an example of a specific data set that you load, satellite image? Is it, how do you define?
Any type of data that has a geographical component.
A graphical component.
Like a location.
What? Geographical component. Yeah, perfect, perfect. A location. That sounds perfect. Yeah, that's one very good definition. Let me get back here. So what about if we generalize this location to something else? What that could be? Like instead of a set of coordinates, what else could that measurement be assigned to? Is it too abstract a question? Like, so you can assign a measurement to a point, or you can assign it to something else, which is, what is it? What is it? A polygon, for example. So you, in general, you don't only assign a measurement to a coordinate, to a point, you assign it to a geometry, to a volume. So we call this the support of the measurement, right? So in geostatistics, there's this term, it's called the support of the measurement, where your measurement is made. Usually in the real world, in the physical world, you make a measurement of a volume. You don't make a measurement of something that is a point, right? Like, so in reality, any measurement you make is a volume. It has like, even if it's tiny, micrometers or something like this, it's a volume. So if we can brainstorm a better definition of geospatial data, we can think of examples, as I mentioned, right? So if you work mostly with raster and vector data, you have an idea of what this data contain. What some of you already say, like polygons, points, right? In the case of raster data, do you know what these geometries are? What are the geometries associated with a raster data set? Instead of being a point, a polygon. So that's the point, right? So
that also depends on the raster, right? It could also just be a distance from a sensor.
Okay, that could be a representation, yes. But the measurement itself is associated to something, to cells, right? And these cells are another kind of geometry, just a quadrangle, an hexahedron. So this is a grid, right? So even though you can represent these grids, these blocks, to reference to another distance to a reference point, the measurements are, of course, are associated with these blocks, these cells, right? And if you go to other formats that are not basically in they are as well in the GIS community, but they're mostly used in the physics community. The people that do physical simulation, they always handle VITEC and PLY formats. These are formats for unstructured meshes. We'll cover some of these examples later. But basically, these formats here, VTK and Ply, differently than GRIB and NetCDF for raster, and different than shapefile and GeoJSON for vector, they also store connectivity information. We will see what this is in a few slides, but basically, you can represent very complicated volumes with very amorphous shapes, and they will be still connected. You know where the vertices are, what the faces are, and you can connect all these things into a cohesive data structure. So for example, if you want to represent the skull of this animal here, or a helicopter, or the Beethoven statue, you wouldn't use a raster, a grid, or you wouldn't use a shapefile or a GeoJSON file, because these are defined for specific geometries, right? So for a mesh that's more complicated geometry, you need a different data structure. So how to connect all these words into a single representation? We need the definition, right? So the definition here is geospatial data, as I'm saying here, is the combination of two main components. A table of attributes, which is usually the measurements you make on each of these geometries, and a geospatial domain. So think of the example I gave before here. You can think that the helicopter model, this geometry here, is your geospatial domain. It's something that you are referencing in space. It's like a domain. And you can break this helicopter into small pieces, triangles, quadrangles, different smaller geometries. And for each of these triangles, you can assign measurements. So you have the domain and the table, right? So the domain is the representation of your physical space, and the table is how you break these physical spaces into small pieces and assign measurements to each of these pieces. So the table has a set of rows. Each of the rows of the table has measurements of different variables for that specific geometry. Is it clear, or is it something too high level still? Does everyone understand? Can I move on? So just raise your hand if something is not clear, because we'll be building on this basic concepts forward. So tables in Julia, right? So in Julia, there are many different table types. And the way that they got formalized is in a package called tables.jl. Tables.jl is not a specific implementation of a table. For example, if you come from Python, you are used to pandas. If you come from R, R has a different name, data frame. They have I think it's built in R nowadays, the data frame. And in Julia, you have many different options. All these options, they communicate between themselves with this abstract concept of tables.jl. Tables.jl is just a way of representing tabular data structures, and they basically mean as you have rows, which are measurements. For example, I have here 5 samples, right? So 5 different people. You have variables as columns, right? So anything that you can think that can be structured into this concept of measurements for different variables is a table, right? So you can just formalize this into different representations. So Julia has different representations for tables. For example, the dataframes.jl package that Iga presented is one. There is csv.jl is a different package that has a different table representation on disk. So you can say csv.file and you give the file name, it will be a table. So it will just understand that that file on disk is a table. There's also different tables that are more, let's say, advanced for people that come from computer science, databases. So you have databases that also implement the tables interface. And so you can access SQL databases or NoSQL databases. All these databases used in computer science can also be interpreted as tables. And so the package tables.jl by Quinn was the one that formalized all these high-level abstractions. And as I mentioned, like Julia comes with built-in tables and non-built-in tables. The built-in tables here are 2. So if you install Julia in your machine, you have 2 ways of representing tables without needing any package. The one is a named tuple of vectors. If you see here at the bottom, that's one example. So how do you create a named tuple in Julia? You just put parentheses, right? And you say, my first column is the column name, which has these values here. You put these values into a column vector. The second column is age, and I put the integer values here as a column, and so on and so forth. So this is the first built-in representation. So if you type this in Julia, you get a named tuple of vectors, and that is a table. So you can make sure that if you check the tables.jl package and ask if this satisfies the tables interface, it will. The second representation is the vector of named tuples, right? So if you go one slide more, you see here that you have, instead of focusing on the columns, right, you focus on the rows. So here I'm creating a vector, so I open brackets and I close brackets, and each of these entries here is a named tuple. So here, instead of constructing a collection of colors, I'm constructing a collection of rows. And if you follow this pattern here of a vector of named tuples, Julia will also, tables.jl will also understand that this satisfies the table interface, right? So what's the difference between these two built-in representations? Basically, when you construct a column-based representation, it's most of the time you do this because you're operating on a whole set of measurements for that geospatial domain. And you usually do operations more often in column measure orientation. But sometimes you want this row measure orientation, especially when you're dealing with streams of data that are possibly infinite, right? So if you are building an API or software that consumes infinite length streams of data, for example, IoT, you go for a row measure representation because it can have infinite length, and you can consume this table row by row instead of having to materialize full columns of data. So what are other types of data? I mentioned already. So there is dataframes.jl, which is a very mature package. It's been there in Julia for a while now. It has top-notch performance. It's very well maintained. And you can see here that the syntax is pretty similar to the column-based representation that comes between with Julia. The only difference is that you add this constructor here at the front, right? So you have the same parentheses, opening and closing, but you put a data frame in before, and then becomes a data frame. What are the benefits for the data frame? It supports additional syntax. So if you create a data frame, you can access subsets of rows, subsets of columns with very convenient syntax like you do in pandas or any other table from other languages. It's very good for data science, and I think it's the go-to package for people doing data science and manipulation. Other examples, as I mentioned, so if you think of CSV, you have the csv.jl package that loads a file as a table. You have the XLSX package that loads Excel spreadsheets as table. So if you work with this format here, XLSX.worksheet, that will also implement the tables interface. So you can directly load an Excel file and operate in Julia as if it was a simple CSV or a simple table without actually converting it into a data frame. And you have these other databases here like ODBC, MySQL, and so on in the Julia databases organization. So the second component, right? So we saw the first component of geospatial data, tables with measurements, and where these measurements are, right? So where these measurements are assigned to, that's the domain. So here in the right, I'm illustrating a domain, which is a domain of the subsurface. This comes a lot in people working in geophysics or working in geological modeling in 3D, for example. Energy companies, mining companies, they do a lot of subsurface modeling. And if you see this here, it's very complicated domain, right? So you see this hexahedron geometries that are deformated, following these folds and all these horizon surfaces that are not very beautiful to represent in a computer, but the mesh can represent this. And so you take this physical region of interest and you break it down or split it down into these geometries, right? So each of these hexahedrons here is a place where you can assign measurements, right? So each of these hexahedrons corresponds to a row of the table we've seen in the previous slides, right? So we got this concept of domain formalized in the meshes.jl module, which is a submodule of a module that I'll be presenting tomorrow on geospatial data science. But this package basically formalizes all kinds of domains and structure meshes, grids, geometry sets, which are basically random geometries without any connection between the geometries. And you can easily look the code there if you want to learn more. It's a very, very general representation of domains there. So the most basic domain that I would like to start with is the one that's corresponding, for example, for you that are familiar with vector data, shapefile, and GeoJSON. how these data sets are usually represented, you have a soup of geometries. In geometric processing, we call this data structure the soup of geometries. Is an informal name for this. It's basically a collection of geometries that don't know anything about each other. You just say, give me a point, a segment, a triangle, a ball, put everything into a bag or a vector, and call this a geometry set. So that's the most simple representation you can get of a domain, right? So you have a region in space, you break it down into geometries and say, hey, this domain is made of a set of geometries. I don't know how they relate to each other, but they're here, right? And you put these geometries here into a vector, the geoms vector, and you wrap this vector into a geometry set domain. So that's how you create a geometry set with 4 geometries. These geometries live in a 2D space, that's why the 2 here, and they have coordinates of type float64, which is how you represent coordinates here in the machine. So as I mentioned, this is usually found in Shape, GeoJSON, all these formats that are used to save vector data. One of the most used ones, I think, that go beyond like a specific community, right? They are everywhere. Everyone doing computer science, doing geoscience, doing anything will come to somehow an array representation, which is just a structured set of dimensions with measurements. So that is the grid format. It comes up with different names in different communities, but it's raster, grid, structure, like so many different names. It's basically how do you represent images, how do you represent satellite images is the grid domain. And there are different, let's say, flavors of grids. The most easy one is the Cartesian grid that we call here. It's basically aligned with the coordinate axis, right? So if you have x and y perpendicular, you're just going to count the x, y in regular spacing and count the y-axis in regular spacing, and then you're going to build your cells. These are the Cartesian grid grids. So you only need to specify where the grid starts, the minimum point, where the grid ends, the maximum point, and the spacing. And you do this per dimension, right? So this structure can create 2D, 3D grids, ND grids without allocating any memory. And that's very convenient. I'll come back to this later, but basically this is a representation that is lazy. So it doesn't consume any memory, it just can represent grids of millions and millions of cells without any storage, basically, right? So that's the idea. And you usually find this in TIFF, GeoTIFF, right? Like raster, like netcdf, grid files. They are structured as grids. There are many flavors, and we have all these flavors implemented in meshes, and you can look it up. But basically, it's a very popular one that shows up in different domains, different scientific domains. What's the most general one? I think the font is super small, but I don't know if I can increase the slide font, but the most general one, I think, in the sense of representation, right? It can represent basically any of the previous domains, is the unstructured mesh domain, and it's a set of connected geometries, right? So basically, it's found in people working in physical simulation. A lot of people use VITEC as the standard format for saving and loading geospatial results, right? So VITEC is very famous. And people in computer graphics also use a lot of these other formats like STL, OBJ, object files, and mesh files, and all these other formats that are used to save geospatial data. So if you think of how you represent this, I will also have an example. It's basically like you only need to get this region in space. I don't know if it's easy to do this with one hand. So you take this region in space, so say I have a circle here, and you can just say, I'll take a specific set of points inside of the circle, save this into a vector of points. These are all the points that I'm wanting to use in my discretization. And I'll just give a rule that connects each of these points. So say point 1 with point 2 with point 3, make a triangle. Point 1, 2, 3, 4, 5, make a quadrangle. And then you can create all this list of connectivities. That's how we call. You get a set of vertices or points together with a list of connectivities, and you build your whole domain. So you have originally any shape you have, and you can discretize this shape into a set of geometries with a list of points and a list of connectivities, right? So that's what has, and that was I tried to show in the example. First, I build a vector of points that you can see there in the top. And then I build the vector of connectivities, right? So I don't know if it's easy to see there, but the vector of points you can create, for example, as a vector of tuples. You just say, here is a vector of 2D points with coordinates 0, 0. The other point is 1, 0. The other point is 0, 1, and so on. And the list of connectivities is this connectivity object also coming from matches that connects integers, right? So I'm saying connect vertex 1, 2, 6, and 5 into a quadrangle. Vertex 2, 4, 6 into a triangle. And meshes will figure out by the number of vertices and the dimensionality of things how to connect this into actual geometry types, right? So if you feed this points and connectivities into a simple mesh, which is the explicit representation of the mesh, you get this domain data structure that has 6 vertices and 4 elements, right? So that's the general representation that can basically allows you to represent very complicated shapes in 3D, and 2D, and so on. So how do you actually get to the final point, geospatial data, right? So we have to combine tables with domains to get to the final representation, right? So that's the purpose of the single function called georef. So there's a function in the geotables package called georef that allows you to take any table that implements the tables.jl interface and any domain from meshes and combine this into a format that pretty much resembles a table, right? So if you look here at the bottom, it looks like a table, but it's a geospatial table, right? So in other languages, we've seen this concept before. It's nothing new. The novelty here is because we unified this for raster vector mesh. Anything fits in the same tabular representation, right? So other packages, maybe Python has, I don't know if it's rasterpy, pyraster. There's a bunch of other packages that do this for specific domains, right? So you have people working with, I think it's GeoPandas for vector data, right? And then there is a package, raster.io maybe, for Python that does the raster part. Here you have one single representation that loads anything, and it behaves like a table every time. There are many optimizations behind the scenes to make it work efficiently. For example, this geometry column here is never materialized. If you have a huge grid, you don't want to create a huge column of quadrangles or hexahedrons. It's just lazy. It looks like it's printing here quadrangles, but it's just like a few first 5 quadrangles or so, but it's never materialized. So this representation is explained in the Geospatial Data Science with Julia book. We wrote this book this year, and it's open access. I can share the link, but if you go online and search Geospatial Data Science with Julia, there will be a link to an open access book that you can read online. You don't need to download anything. It's just where these things are explained in much more detail. I'll be calling this book here in GDSJL for short. So if you see GDSJL in the slides, it's because it's a reference to this book. You can see here one of the first things that I would like to point out in this representation is that it's aware of many useful things for data science. So the first thing it is aware of is the scientific type of the columns. So if you see here below the names of the columns, name, age, height, gender, and geometry, there is a subheader of scientific types. It recognizes that the column of strings is a categorical variable. The column of age is a continuous variable because I gave the units of years. This is a time unit. And the height is in meters, right? So it knows it's also a continuous variable. Male or female, the gender, it understands that it's categorical. And you see it in the third subheader that it has no units assigned. So this representation is very robust in the sense that it knows scientific types and it knows units.
Where did you get the units? As in, where did you input the units from?
It's very small, right, the font? So if you see here in the column, there's a U after the vector, so unit year.
So unitful.jl.
Unitful.jl, yeah. So there's a package in Julia, good question, Natal. There's a package in Julia called unitful.jl. That's the package, one of the packages that supports units in Julia. So if you want to express your physical measurements with units, meters, I don't know, meter square, kilograms, the metric system, any units you can imagine, the unitful.jl package is the more mature package. There are alternatives. Dynamic quantities.jl is another one that you can assign units to raw numbers, right? So We have integration with Unitful so far. Unitful.jl is the one that is integrated in the ecosystem, and we can definitely add support for alternatives as well. So basically here you assign units, as Netino asked, the column here, age, I put the numbers, and I put the suffix here, UYR, it means the units of year. And in the bottom here, I say height, I give the numbers, and I say the units are meters, right? So it's very good to work with units. It's actually very good practice because you can catch a lot of bugs just by putting units there. So if you try to add inconsistent units, there will be a runtime error, or even sometimes maybe a compilation error when you try to do so. So you see, like the table, this geo table here has the names of the columns, the scientific type, continuous, categorical, textual. There are a bunch of traits that are available in the data science traits.jl package. And it has the notion of units as well. That's very useful, and it tries to propagate these units in the geospatial data science stack as much as possible. Okay, so that's like the overview of what the geotable is. And you can see here also another useful information. The header here shows that that's a 4x5 geotable, 4 variables by 5 columns, right? Because the geometry column is considered a column, over a 2x2 Cartesian grid, right? So you see that the domain information is not lost. It knows that this is a grid, even though the geometry is showing as a set of random disconnected quadrangles, you still see that this is a Cartesian grid. So what are the benefits of universal representation? Let me see how I am with time. Okay, what are the benefits of a universal representation? People from different communities can interact and work together. My goodness, how hard it is. We are 2024 and like climate people, earth science people, geoscience, they cannot talk to each other in software. They're just like doing their own stack, separating GIS from 3D modeling. It's just unbelievable. Like I really hope that people can buy this message that we need a universal way of communicating between software stacks and communities. So consumers of this geotables representation can leverage an extensive ecosystem for geospatial data science because geotables is one module of a much larger ecosystem. And this ecosystem is native Julia. It's written 100% in Julia. So if you go, I'll have a talk tomorrow that goes over a specific bit of this. It's one chapter of the book. But it's 100% Julia, so it's flexible, it's performant. There are corner cases, of course. We are working on the optimization of performance whenever it shows up, because we cannot handle all corner cases with a small team, right? But we make sure that it works correctly, and then we optimize for performance. So if you are curious about how these things work, if you want to contribute, you can just open. It's simple Julia code. There's no Fortran, there's no low-level pointers pointing to memory. It's like very high-level Julia code. More features to end users, right? So if you adopt something like this in your stack, so say I have a simulation solver, a physical solver that outputs geotables or consumes geotables with properties. Say you are working in the subsurface, you need to consume maps of permeability, maps of conductivity, maps of wind speed, whatever. If you consume this as geotable and you run your simulation and you produce a geotable, you can right away have a ton of features for you, like visualization of these tables is already implemented. You have all this geospatial data science stack for you, so if you need to do post-processing to clean data, manipulate it somehow, do aggregation, run a machine learning model, everything just works. You can just feed this geotable to the stack, it will just work all the way down. So it's very nice to be able to interact with this table after you have it constructed. And we will show here in this deck of slides as well that we have integration with all these file formats. Right? So we support more than 20 file formats already, all these formats from GIS like Shape, GeoJSON, NetCDF through the backends. Alex is one of the maintainers of the NetCDF. All these formats, VITEC, they're all backends of this package called GeoIO that will load the data in the particular data structure that it loads and convert into a geotable for use, right? So if you care about just loading the data to get your work done in your scientific domain, right? So if you have a scientific question that you want to address and you don't want to waste time learning different underlying representations, you GeoIO it, get the geotable, and start working. And it is integrated with Maki. Simon is also here as the maintainer, one of the main maintainers of Maki, which allows you to do very high speed interactive 3D visualizations. We'll see some of this as well. So I don't know how much time we have for the live demo, but I will try. I have 10 minutes, so I'll just go example by example here. So here's how you see. I can share the script as well after the talk. I'm loading 3 packages in this example: meshes for the domains, geotables to take domains and tables into a geotable, and GeoIO to load these tables from disk in different formats, right? GeoMaki is the Maki backend for visualization. So you see some visualizations in this example here. So I can load these packages, right? So I'll just press Alt-Shift-Enter, and then I'll create my first geometry set here. I'll create a point, a segment, a triangle, a ball, and put everything into a geometry set. You see here in the right, the same example we saw. And then you can call this vis function, the vis gset. And this vis function here, my tablet is not very powerful. It will just open a plot where you can interact, you can zoom in, you can create boxes. It's just because I'm on here. You can create zoom, and that's basically like all that Maki has to offer, right? So if you create these 4 objects, there's a point here, there's a ball, there's a segment, there's a triangle. I can then visualize this geometry set with different colors, colors 1 through 4, right? So if I execute this one, you see that I have different colors for these geometries. I can then fix the data aspect, right? So by default, the data aspect is not the data aspect, right? So it's, you create this, and you see that this ball is kind of an ellipse, right? In order to make it a ball, you have to change the aspect of the plot to be a data aspect. So if I execute this one, you see now that everything is in proportion, right? So the ball is an actual ball, and all these lengths are corrected, right? I can also add other things to this figure with the vis exclamation mark. So I can add the boundary of the ball in the color red. So if I execute this cell here, you see that the circle has a boundary in red. And I can also add the boundary of the triangle in blue, in black, right? So I can customize a lot of these details for the final visualization. So how the geotable works now. So here I created my domain, right? The geometry set, 4 disconnected geometries. One thing I can do is just convert into a table that has no measurements. So I assign a nothing table. So I just say, connect this nothing to the domain. That means I don't want to assign any measurements. So you see that it creates here on the right a geotable with just the geometry column, right? So the screen is not ideal, it's very small here, but you see that there's a geometry column, and that's it. Or I can assign a table, right? So I can say here I'll create a table with a column A with integers 1 through 4, and a column B with random floats. And I will assign this table to the G set. If I do this, you see that, let me increase here. You see that, I will just execute like this. I think it's easier. You see that there are 3 columns now. A and B are features, are values. They have this pink color, and the geometry column is special. We color it green, right? So it's just to differentiate between what are columns of measurements and what is a special column of geometries. You see that it recognizes that integers are categorical and floats are continuous, right? So if you want to change the scientific type, you have ways of doing this, and we will explain some of this tomorrow. Let's come back here. So this geotable, as I mentioned, it's very clever sometimes with the ways you access the sub-data sets, right? So if you say, I just want the first 2 rows, so I say 1 through 2, all columns, right? So if you do this, it will never materialize the domain, right? So if you had a huge raster, huge grid, it will just take a view into the grid, and it will never create the subgrid because that allocates a lot of memory. But you see here that I have just the 2 first rows and the 2 first geometries, right? Point and segment. You can access the columns with the syntax geotable.column, right? It pretty much mimics what the dataframes.jl package does. And you have this other easy feature here, which is the viewer. You send a geotable to the viewer, and it will try to build a viewer for quick inspection, right? So if I say here, send the geotable to the viewer, you see that it creates this, let me zoom here. It creates this scene here where you can see all the variables that are in this data set. So there's variable A is categorical, with 4 categories in the color bar. We need to use the new Machi's ecosystem for categorical color bars. And then if you change the column B here, it changes the color bar to a continuous color bar, right? So you see here different variables over this geospatial domain, and you can interact with the menu, you can zoom, you can do anything that Machi supports. Here is the grid domain. Let me see how much time. Okay, here's the grid domain. If you create a grid that's 5 by 5, you see here that it's represented like this, right? But if you visualize this grid, it's just a different domain, right? I can just give colors 1 through 25 because a 5 by 5 grid has 25 quadrangles, right? So if I just do this here, it creates this raster, right? So it's a set of 25 quadrangles, each of which has its own color, 1 through 5, starting here at the bottom left, ending here in the top right. I can also fix the aspect of this plot so that it looks like a square grid, right? Because now the coordinates are meshing in length here in the screen. And you see that this is a Cartesian grid with 5 by 5 quadrangles. It also works in 3D. You can just do it later with your own example. Here I'm calling this, and I'm asking for this option here, show facets. And show facets will just show the boundaries of each of this cell, right? So if I just say show boundaries, it will show these edges here, and I can also set the color of the edge if that's useful. So I'll just change the aspect again. I'll create here with color, and I'll pass facet color equals red. So if I change the facet color to red, it will show the facets in red now. It's very customizable, right? So we're trying to get more and more customization of this with the ultimate goal of having a unique set of aesthetics options that work with any domain. So that will facilitate you writing a script once and just loading in geotables over vector or raster, anything will just work the same. What else? I have here this other option, but I think it's more domain specific. If you feed to a grid of 5 by 5 quadrangles, a vector that's 36 long, that is 6 times 6. It's because you're assigning colors to the vertices instead of the quadrangles, right? So what it will do, it will call the Machi function that does the interpolation in the graphics card, right? So it will just, let me actually do this here. It will look more smooth, and that's because I'm assigning colors to vertices and letting the graphics card do the interpolation, right? So it's sometimes useful to show this data like this because the fields you are mapping are usually continuous, right? So they're not just greedy-like visualizations, right? So that's an option that's also explained in the docstring, but it's more specific to specific type of workflow. Here I'll create another table. See, I'll create a table that contains the centroids of the grid. The centroids of the grid are just points, right? So I'll create this table here. And it knows that the centroids are these 2D points, and I can then georeference this table to the grid. And you see that it has the centroid as a column, so the columns can hold anything, basically, because Julia is dynamic, it supports this very high-level abstraction. It's not like pre-compiled to only support integer or float. It can support any type that you feed here as column. And in this case, the column of centroid is like a column of points. It shows as a tuple, but it's actually a point. But you can have any sort of measurement. So if you need to save vectors, matrices, or any tensor in your triangles of the mesh or in your raster file, you can. Here's the example of the mesh. I think it's the example in 3D. So I create a mesh, a sphere. You see it's a primitive, right? So I create a sphere with center and radius. And now I can do this discretization of the sphere into a mesh. So here is discretize the sphere with regular discretization, where the first dimension I want to 30 elements, and the second dimension I want 50 elements. And if you do this, it will create the mesh of the sphere, right? So you see here that this mesh has 1,500 vertices, and it has how many elements? Let me just write it down here again. It has 550 elements, right? Quadrangles and triangles. So I can visualize this mesh as well. Oh, sorry. I can visualize this mesh. Just go here. and it will show the mesh with the 3D Mach scene, right? So if I can zoom here, this is a mesh of the sphere. You can zoom in, and you can imagine that sometimes you may be working on the whole Earth as a sphere or as an ellipsoid or something like this. You'll be able to flexibly visualize this and assign measurements to each of these quadrangles or each of these triangles here near the poles, right? So there are many options to highlight and color this. For example, I can assign this, the area of each of these quadrangles on the sphere to this table, right? So what I did here, sorry, the code is so small. I created a geotable where I georef the area of each of these mesh elements. This dot here applies the area function to each of the elements of the mesh, and then assign it to the mesh itself. This creates the table. And if I send this geotable to the viewer, you'll see that the sphere has these elements that are colored now with their area, right? So the elements near the equator here have this, in this discretization, have this higher value compared to the area of these triangles here at the poles, right? Now the last bit, I'm on time. The last bit is the GeoIO module. So the GeoIO module has two functions, nothing more: load and save. Load any format. So here I'm loading a mesh in STL format. That's a format from the computer graphics community. And that will load the geotable, right? And I can just visualize the geometry column, right? So I can just visualize this geometry. Where is it? Here. And it will load this airplane model, right, that is available online. And so some people may be using geospatial data science not for Earth, for geoscience. They may be using it for engineering purposes, right? So if someone wants to load a mesh model of a plane, do physical simulations, and do some post-processing on the fields over the plane, how to do that? We facilitate this through this tech, right? So if you want to benefit from this, just adopt the geotables format. You get this for free, right? So now that I loaded the geotable from STL, I can save it as object, I can save it as off format, I can save it as mesh format, and these are different formats of unstructured meshes that are supported. I can also load a TIFF file, a geotiff file here, right? So you see if I load it, let me increase here. Let me execute this here again. It has 3 variables, band 1, 2, and 3, and it has the geometry column. It's cut here from the screen, right? But you can do the same here. My tablet is not powerful, so it will take a bit more time here. So if I call the vis function on this geotable, it will perform the transformations that are stored in the geotiff and show the geotable as a raster, right? Because if you see here at the top, this is a geotable over a transformed grid of that many quadrangles, right? So if you see here, it loaded this raster, this rotated raster, like it applied the transformation, and you can zoom in and do all your analysis as you usually do with other plotting frameworks, right? But can you also what? Select the band? Oh, that's not the... Oh yeah, so if you have multiple variables like here, band 1, 2, and 3, you can send it to the viewer. Let's see if it works here. Because they're categorical right now, right? So geotable has 3 columns. I can just send it to the viewer. It should be able to show the 3 of them with the menu as well. Let's see. The problem is that categorical, I should, before I send it to the viewer, I should actually reinterpret the categorical as continuous, right? So there's another transformation called coerce, that I should coerce band 1, 2, and 3 to be continuous in order so that it doesn't try to plot this variable as categorical. Because you see, categorical color bars with thousands of categories will be like very ugly. It will show up soon. It's just taking time because it's a huge color bar with many categories. I should have converted these categorical columns to continuous first. So here it is. You see that, yeah, it's taking more time because it's trying to plot like thousands of categories, but it's a continuous variable saved as integer. I should coerce. So how you do this, we'll see more of this tomorrow. So I would say geotable and then coerce the columns, whatever, to a data science trait, so continuous. I'll show you more or less what it is tomorrow. It's not this specific code, it's almost like this. It will convert all these 3 categories to categorical variables to continuous so that you can plot it as a continuous field. And And that's it, basically. So that concludes the talk. I hope that you guys got the main message here, which is we are trying to really fight hard to this universal representation to benefit different interaction between different ecosystems and communities. And I think lots of it is already polished. We need some work on making some of these visualizations more efficient, maybe some help from the Maki team to call the right Maki functions with the geotable domains we have. But everything is very polished at this point, so I hope that you can just take a look at the book. I'll open it for the final here so that you have more things to see here at the end. So let's see. If you want to learn more, so that's the final slide. The book is the resource, I think that's the more organized one. So Google Geospatial Data Science with Julia, we call GDSJL. It's the book that has 3 parts. Part 1 is foundations, you'll find some of this there. There's part 2 on these queries and transforms, and part 3 I think is queries actually, and part 4 is applications. There are some chapters that are missing, we're still working on them, but most of the foundational work is already there. So if you read the book, you'll be very prepared to get used and start using this stack. You have the Zulip channel as well if you want to have more support after the conference. There's the geostats.jl support channel on Zulip. It's one of the platforms that the Julia community uses to interact. And if you want dedicated support, consulting services, just contact me. I can also help integrating some of this stack and working out specific issues. And tomorrow there will be another talk specifically on the geostats.jl stack, which is how do you take these geotables, process, visualize with more advanced transformations. That's it. Do you have questions? Yeah?
Yeah. First, thank you for the talk. It was really great. I look forward to trying it out. Do you also have coordinate reference systems? Is that part of the 2 things?
Yeah, so we are working, that's the plan for the next semester. We are planning to integrate coordinate reference systems in a better way. So far, we are not explicitly modeling coordinate systems, and I was also talking to Magda there. So we want to integrate more of the geodesy coordinate system work so that it's more smooth to end users. We don't want to ask end users to learn geodesy on all this complicated stuff because most of the time the scientists just don't want to address the scientific question and not know what's the CRS of this table, the CRS of that, and everything crashes, so it's not compatible. We just want to hide this, and we need careful design for this. We're planning it for next semester.
You said that the geotable is able to read NetCDF as well. Does it include NetCDF? Does it also include NetCDF files that are not necessarily longitude, latitude based, but more like time and height based, for example, like dimensions that are not longitude, latitude?
Cool. So we are using Alex package on NC datasets and GRIB datasets to load these datasets as backend, right? So anything that the package supports, we support. But we also require the, what's the name of the convention? CF conventions? What's the?
Basically CF conventions,
So the
right?
assumption here, in order to load the table without any additional keywords that are specific to the data set, we only support CF conventions. You're saying, here's the geotable. If you want to use GeoIO directly and just provide the file name, adopt the CF conventions. If it's something that doesn't follow the convention where the variable names are well-defined or something like this, we just ask the users to go to the backend package that has more flexibility to load this in a different way and do the post-processing into a geotable manually.
All right, thank you.
Any questions? Alexander, vais atrás? Espera só um bocadinho.
Thank you. Thank you for the microphone. Thanks for the.
Hi,
Is this on? Thanks for the great talk. I was wondering, in your split apply combine engine that you use, do you use data frames under the hood, or do you have your own
own macros,
engine?
yeah. We developed our own macros in order to avoid the materialization of the geometry column, because that's expensive, right? So we have the group bys, transform, and combine. They do a clever job with the geometry column, basically. So they do the traditional split apply combine, avoiding materialization of the geometry.
Okay. And so, so you're not using data frames for
No,
this, right?
no.
And did you make some benchmarks to see? Because I think the data frame is really, really efficient.
really,
So
really
I'm just
fast.
wondering if you made some benchmark to see.
No, we didn't do any benchmark yet because, as I explained, it's like so much work to already get it working correctly, right? So we're focusing on making the stack work correctly, and then we will fix these performance issues as they come, because it's a small team, we don't have enough time to cover all the applications and use case. So usually, like, if someone finds a bottleneck, a performance bottleneck, just report it, we try to address, or even contribute a PR. We are happy to review and merge.
Okay, great, thanks.
Questions? No? Okay.
Thank you.
Thank you very much, Julio.
No problem. Let me just disconnect here. Sorry, so many things. I think I'm done.
Do you want to? Okay, so now we will have a talk by Nathaniel Wong called Introduction to Julia, Creating Packages for Earth Observational Work. Nathaniel is a 5th-year PhD candidate at Harvard University studying tropical climate using a range of observations, reanalysis, and modeling tools. He has developed a few Julia packages, such as georegions.jl and nasaprecipitation.jl, to help with his work that requires retrieval and use of Earth observational datasets. He also used Julia to analyze model output from WRF and SEM. Okay, thank you. You need something?
No, I'm fine. I think I'm fine. All right. So, afternoon, everybody. Just a question. Who here is touching Julia for the first time? Okay. And who here has not? Those of you who have used Julia before for the past longer than a day, how many of you have tried creating package? How many of you have not tried creating packages before? How many of you have no experience in creating packages? Yeah, in Julia, no experience in creating packages in Julia. Okay, so yeah, this talk is meant to help people understand the basics of package creation in Julia. I will be going through a few more basic concepts in Julia as well, such as environment and project management in Julia, so that, and how to install, basically how to install packages, how to update packages, how to basically do what you need to do. So basically, for example, just now, Julio was introducing the geostats geotables package, but how do you install the geotables package in Julia? Because a lot of these packages, most of the packages that we will be talking about over the next 4 to 5 days are not actually packages that come with Julia. They're not inbuilt into Julia. You have to add them, well, they're registered as part of the Julia ecosystem, but you need to install them, you need to select them and install them. It doesn't come with the Julia that you downloaded onto your computer. So this presentation also is mostly geared towards Linux and Mac OS users because of the heavy usage of terminal. For Windows users, I recommend the usage of Windows Terminal, or at least being able to run, or at least if you have an alternative that's able to run Julia on the command line. So if you like being able to use command line features or terminal features to go into folders, to create folders. For example, let's see. Okay, so for example, like a terminal window like this, where you can go into different folders, where you can run Julia, for example. If you have a Mac or Linux, this should more or less be relatively easy for you. If you're on Windows, is there anyone here who has been using Julia for a while who is using it on Windows? Yeah, so might I ask you guys for help in this case, to help later when I'm doing terminal sessions to help with running Julia on terminal, for example, okay, thank you. So got that out of the way. Okay, so and it's also because I also think it's good. Well, I wouldn't say necessarily best practice, but from my experience, if you don't know how to use Julia from terminal, there's some stuff, or if you're not comfortable with using Julia on terminal, it can get a bit tricky when you're trying to manage your package environments per se. Like or at least for me, I'm used to setting up Julia in my project environments and then running them in the respective files, for example. So it's good to know how to use terminal when you're running Julia. It's actually good to know terminal when you're running Python, for example, as well at the same time. And one more additional thing. Later, if we have time, because I know my lecture is 2 hours, but there's a lot to cover. If we get to this part, the notebooks that I will be using can be found on the GitHub repository here. I will flash the link later as well when we get to that part again. But it's just online, and if you want to look at the notebooks after the lecture, you can also download them after the lecture and fiddle around with the notebooks as well. Yeah. So the aim of this lecture is that we have to understand that the Julia community, compared to the Python community, is relatively small. So we don't necessarily have the wide, extensive community that Python has when it comes to package development. A lot of packages are therefore developed by individuals, like Alex, who developed NC data sets, like Julio, who developed the Julia Earth community, and for me, like I developed georegions and NASA precipitation, etc., etc. A lot of us are doing this as individuals that are trying to help the wider Julia community for Earth observation. But the fact is that because we're all individuals, our attention span and the amount of effort that we can dedicate towards developing packages is limited, and we can't develop packages for everybody because we are developing packages for ourselves as well. So the thing is, much of the development of Julia in the earth sciences requires individuals like you who are also just newly starting out in Julia to also come in and help with package development for your own specific needs as well, to help mature the Julia ecosystem in earth sciences, in earth observations, etc., etc. Like all these packages that are here that we're talking about today, tomorrow, few days in the future, they're all developed by individuals who started out maybe a few years ago. I personally started using Julia in 2020, and there's still a lot that I need to learn as well. But I'm here to try and share some of the pitfalls that I went through in developing packages so that you won't go through those pitfalls again. Yeah. So to develop a package, you need to understand the basics of Julia environments and package management, and also package development in Julia. So the outline of today's lecture is going to be first understanding and managing the package ecosystem, and then we're going through creating packages in Julia. And then if we have got a bit of time, I will also be going through the package, my package georegions.jl, both as an example of a package that has been developed over the past 3 years, because I've been working on georegions for the past 3 years, and also some Earth observation packages, Earth observation application usages of georegions.jl. And if we have time, if there's time in the next 2 hours, assuming we don't run out of time, we can talk more about developing packages for your own use cases as well. Yeah. So this is a more detailed outline. Maybe I'll just skip it for now. But the thing that I want to get to is the Julia package ecosystem. So the Julia package ecosystem and the concept of Julia environments. So basically, when we're talking about an environment, it is, in my opinion, a bit similar when we're talking about Conda environments, except that the Julia package environment is a lot more developed, or not, is a lot more streamlined and a lot more seamless than using Conda to manage your package environment. So when using Conda to download, so think about when using Anaconda to download a package, and then Conda, when you ask it to install this package, it will also install all the dependencies for you, etc., etc., etc. Julia has an inbuilt package manager that allows you to do all that without needing, and in my opinion, it is much better than Conda. So because of the way packages are built and packages are registered on the registry, the package ecosystem in Julia is a lot better able to handle conflicts in dependencies, and it's a lot better in telling you when something is not compatible with another thing, for example. So that's what a Julia environment is. So a Julia environment is defined by two things. One is the project, and one is the manifest. So in any project, if you see on the screen here, any project here that you see is defined has a project.toml and a manifest.toml. So if I go into, so this is, let me escape this. Escape. Okay, so if I go, so basically I'm in my projects folder and I have a lot of different projects, for example. If I go in, all these projects are Julia projects, by the way. So if I go into any of these folders, for example, and I list, you will see that there is a project.toml and manifest.toml. So what these projects and manifest.toml do is that they define what packages are inside your projects, for example. So for example, if I look at what the project.toml is, the project.toml, the dependents, all these are the list of packages that I am currently using in this particular project. And if I go to another project, let's go to Sumatra Squalls, and let's look at this project list again. You will see that the project list is slightly different. So for each of these projects, for each of these projects that I have a project and I have a manifest, and when I install, and when you're using these projects, for example, in each of these projects, you should have a separate environment for each of these projects where you will install all these dependencies independent. So if you install a package in project A, it is independent for installing the same package in project B, for example. So if you have two different folders with two different projects, installing your package in one project will not affect the project you will not affect other projects that are independent, for example. Does that make sense? Is everybody following? Yeah. So that's the basics of what a project is, and for every project you should create a different environment. Yeah. So just now I showed you the project.toml contains your package list. It's always necessary. It also contains compatibility bounds of the packages. So if you see, here you see compat means compatibility. So you can define the range of the. So for each package, it is possible to define what version of the packages you want in that project. So for example, if you want version 5 and not version 4, because your project requires that you use version 5, you can set the limit to be version 5 instead of version 4, for example. And more information on what projects and manifests are can be found if you search if you go and search for package.jl. Package.jl is basically the package manager. It's basically the package manager for Julia. It is inbuilt into Julia. But the documentation there will provide you with a lot more information that is necessary to understand the handling of your environments inside, for example, in there, for example, yeah. So going back, we've covered project.toml, okay. And with your project, you can also define your project name, for example. So for example, the name, that one is convection isotopes, the other one is NASA precipitation. That's the name of your project or your package, for example. Yeah, this is for compats. You can specify the compatibility of the versions in your projects. The second one is manifest. So basically, a project is necessary to define the packages in an environment. If you want to share a project with someone, you at least need to share your project.toml with that person so that when they compile the project, Julia will automatically download all the necessary packages for you. What a manifest does is that a manifest specifies what exactly the versions and the links of the packages are on your personal computer. So if you upload the manifest.toml and you give it to someone and you compile the project with a manifest.toml, in actual essence, they will be installing exactly the same copy or the same versions of the packages that you are using on their computer. Basically the exact versions that they install on the computer will be the same as what you have installed on your computer when you uploaded your manifest or you gave your manifest to them. So a manifest is not strictly necessary in order to share a package, in order to share a project with someone, but it is necessary if you want to share a project with someone and you want them to be able to reproduce the same results that you got on your computer. So so that's the difference between a project and a manifest. You must always have a project, like I said. And if you don't, if you don't have a manifest, when you compile the environment of your project or your package, Julia will automatically create the manifest for you. So your manifests between different machines, different computers, even for the same project, can be quite different depending on where you're pulling your packages from, what versions you're pulling your packages from. So let's see. Here, so for example, if you go and if you download georegions.jl, so this is georegions.jl, you see that here, oh, sorry, I have to keep exiting the presentation, I'm sorry. Okay, so you see here that this is the package georegions.jl. If you enlarge the screen, you see that when you create a package and when you upload it to GitHub, you don't upload the manifest as well. You only upload the project. So let's clone the project. So cd git clone this. Slow. Okay, fast. Sorry, it's taking a bit. Never mind. Let's basically go to georegions.jl, and you see it's not loaded. Damn. Is it done? Yes, it's done. Okay, georegions.jl. You see here that you only have the project.toml. When you activate and you pre-compile the environment, All right, it's compiled. You see that you have created a manifest. So so you can create a manifest on the spot through compilation of the environment. So only a project.toml is strictly necessary if you want to define an environment, if you want to define a package or a project. So yeah, that's what I showed you just now. So that's basically the upshot of what an environment is. An environment is basically project plus manifest. But the project is where you define, is where the information of your packages is saved, and manifest is what exactly those packages are. So we got a few activities for those of you who are new to this. Now your turn to try and create an environment. So if this we require the usage of terminal. So if anyone has, okay, this requires the usage of terminal. So, so we can go through this step by step. So if you want, so basically the first step is that just create a random folder in wherever. Okay, sorry. You create a random folder wherever. Test. Folder, and you go into test folder, right? You go into test folder, and then you run Julia in this. In this folder. So when you run Julia in this folder, sorry, you should also know that there's nothing inside this folder right now, right? Because I haven't defined anything in this folder. When you run Julia in this folder, and then you proceed to act. So basically, what happens is that this is what you see when you just start up Julia. When you just start up Julia, and then you press the in order to enter the package console, in order to enter this version 1.9, what you have to do is you have to do this. You have to enter this part. You have to do this command over here, this one here. Do the right bracket, the right square bracket. Press the right square bracket. You should be able to get into the package environment. Has everybody reached that step? Okay. So, and then after that you do activate dot. Activate, so dot means current folder. So activate the current folder, you're activating a new project at the current folder. This is what you're doing. You activate dot, activate space dot. You activate the new project at this current folder, and then add a package, add a random package. Say you want to add geotables, add geotables, for example, and see what happens. You add geotables, and this should be what happens. So when you add something, and then it compiles and then it pre-compiles something, and it will install all these things, and then it will store all the dependencies of geotables for you. So what you will see, okay, let's see how long it takes to compile. Okay, so geotables is the only package install, so geotables is the one at the end. Okay, so when you see status, status means that you are viewing all the packages that you have installed in the project. So you've only installed geotables in for this particular project in project.toml. So in project.toml, it only shows geotables version 1.14.3, for example. You go out of Julia, you exit Julia, and then you list ls, everything that's in the folder. You see that Julia has automatically created a project. Let's see. Julia has automatically created a project and a manifest for you. And then, if you look at the project only contains one package, which is geotables.jl. But if you look at the manifest contains a lot of different things, and all these different things are the dependencies of geotables. So everything that you need, all the packages that are needed for geotables to run is listed in the manifest. Is listed in the manifest, yeah. So that is an example of how you create an environment or an environment from scratch. So basically, when you go back to this folder and you activate this environment, you can, so basically this is a completely new environment. This is a completely new environment that you have just created. The first environment that you have created. And if you go back to, you must, and always remember, you must always activate the environment first in this folder. You must, in order to modify the contents of the project.toml in this particular folder, you must always activate the environment in this project first. Like, and then you can do whatever you want with it. Like you can add your regions, or you can add another package, for example, or if you want to remove, or if you want to do other things with it, that's fine as well. But this is the environment for the project itself. If you want to go back to the master environment, which is the main Julia environment, note that you have just installed geotables in this particular environment, right? But when you go back to the master environment, the old environment, the main environment, you will see that this is the list of my projects this is the list of my packages in my main environment. I do not have geotables installed because geotables is only relevant for that first environment that you have created, for example. So this is an example of how you separate out how you can separate out one project from another, for example. This is also why when we are talking about using Julia, it is always encouraged to use, it is not encouraged to use the main Julia environment. It's always encouraged to use your own project environments that you have created yourself in order to run your own scripts. Yeah. So that's basically how you create an environment. Is everybody following? Everybody's following? Yes.
How did you enter in the package mode?
Enter in the package mode is using this command. So basically, right square bracket. So this is the normal one. You see Julia over here, like this. You see this where my cursor is blinking. You have Julia and then the right arrow, right? Then you press the right square bracket. Press the right square bracket. You should automatically get V1.9, V1.10, or something like that. Everyone got that? Yeah. Okay. So, so that's how you enter the package. That's how you enter the package console. Everything good? Yeah. All good? Yeah. And did you manage to follow the rest about the creating the environment? Yes. Okay, good. So that's how you create an environment from scratch. But what about if someone wants to share their own project or their own package or their own project with you? Because package you can just download from, you can just install it. If they want to share a project that they already have created with you, okay. So this is the one. So basically, this is an example of pre-compiling an environment that someone has shared with you. You can go to this particular repository. If you want to go to this particular repository over here, let me leave this link up first. Okay, so let me leave this link up for the next 30 seconds so you guys can go to this particular link. Everyone good? Got to the link? Everyone got to the link? Okay. So the next step that I want you guys to do is to clone the repository. Is to clone the repository. Do you guys know how to do that? You guys know how to clone the repository? Okay. So I'll give you guys maybe another half a minute to clone the repository into wherever you want to clone the repository to. Everybody clone the repository already? Okay, so if you go into the repository, then you should be able to go into Julia and activate. You should go into Julia and activate the environment. And then after that, if you click on status, you see that there's all these. You should see that all this, and then you do pre-compile. All right. So that's how you. So when you do that, that's how you pre-compile. That's how you compile an environment that someone has sent to you. I did status just to show you guys the list of packages inside. Just list of packages inside this project, and then after that, I did pre-compile, and then it compiled the environment. And then after compiling the environment, you see status. And then if you look at status, you should also be seeing that there are some green arrows here, and then there's a yellow arrow here as well. So the green arrows and the yellow arrow here mean that even though you have installed the packages for this particular environment, the green arrows mean that there are updates to the packages. There are updates to the packages. To the packages that are in this particular project. It's just that the manifest when you compile when you pre-compile, you're pre-compiling based on the manifest. So the manifest asks you to install these old versions instead. And that's why you have the green arrows, because the green and the yellow arrows, because these packages are updatable, or there are new versions of these packages, and the green ones represent packages which are updatable. So if you update, you see that you are going to update several of these packages over here. So you have several of these packages that after I press update, it will automatically go and find new versions of these packages. And then it's compiled, and then if you go back, git diff. So you see git diff. So basically you see that git status. What I have done after I have updated the packages in my environment for this particular project is that I have modified the manifest inside this environment, because even though nothing has changed in the project, the same packages are being used. The same packages are being used, but the versions are different. And because the versions are different, you are modifying the manifest. So this is an example of why when people, or at least this is especially true when you are trying to reproduce results from an old study maybe 1 or 2 years ago. if you want to exactly reproduce the results for the old study, sometimes it is best to just pre-compile and not update your environment, because to pre-compile your environment, if you pre-compile the environment, you're using exactly the same versions of the packages that the original author was using to get the same results. So if you update, you are using new package versions, you might not necessarily get the same result. So this is important to understand if you want reproducibility for project and for project purposes, for example. Yeah. So this is fiddling around with Julia environments. I think this is particularly necessary if you want to understand how not just creating projects but also creating packages, because you have to understand in understanding the Julia environment and how projects because for the difference between a package and a project in general terms in Julia is that at least in my definition, a package means that you have the project. It means you have the project.toml, but an actual project means you have both the project.toml and the manifest.toml. Because what you want for a package is you want it to be generalizable. You want people to use it for various different use cases. So because a lot of people will be using it for different use cases, they will be using it alongside many other different packages, for example. So the exact dependencies of your package, or the exact dependencies will change slightly for your package, but because your package is supposed to be general, it's supposed to be general enough, reproducibility is not so much of a factor in this case. Whereas for in a project, reproducibility, especially if you want to share your results, reproducibility is always necessary, which is the difference. So now let's get a bit more into the actual creation of packages. So when you want to create packages, most of us, when we create packages in Julia, we use this package called packagetemplates.jl. So packagetemplates.jl is basically a package used to create other packages, basically. So it's basically a package that is this package is basically meant to streamline the process of creating new packages. So when you use package templates, it will immediately set up the folder structure for you. It will set up documentation. It will set up how you can do documentation. It will set up the necessary Julia files for you. It will give you, it's basically a template, which is why it's called package templates. And then what happens is that it will set up by default a package environment to create both the project and the manifest. To create both the project and the manifest, but it will only track the project. So when you push your package to GitHub for registration, it will only push the project to the GitHub and not the manifest. Because for a package, you do not want to push the manifest to GitHub, because the goal of a package is not to be specific, but it is to be a general use, for example. Yeah. So okay. So the compact requirement, because when you look at a package, for example, this is the georegions.jl package here. This is, if you look at the project.manifest, you will see that this is the name georegions. You see that there are dependencies as well. But when you want to register a package in Julia, your compat bounds or the compatibility of your dependencies must be clearly specified. If you don't have this section, you will not be able to register your package in the Julia registry. So the compat is necessary. The compat is very necessary. Is a necessary part of the project.toml, which defines the versions of the dependency packages. that are necessary for to work to make your own package work. So yeah, this is the compat. So you want flex, and then but the thing is, because you already have this compat, you also basically want some flexibility in your dependencies as well, because your manifest.toml by nature, especially if you keep updating the manifest, if you keep updating your package, or if you keep updating your project, for example, your manifest will keep changing very, very, very rapidly. So that's why you generally that's also generally why you do not want to commit your manifest, because the manifest just changes too much. You only want to commit your project, where your project will define a range of versions for which your dependencies can fall under. So for example, in this case, georegions.jl depends on, for example, geometry basics. But for geometry basics, I only want it to, I only allowed versions 0.3 and 0.4 in the compat. So when I install georegions.jl, it can only install either 0.3 or 0.4. It cannot install 0.1 or 0.2, for example. So that kind of hard limit is also set in the project.toml. That's why generally a project.toml is enough when you are creating a package, or enough to track. So this is about personal projects. I don't think it's strictly necessary for now, since we're about 50 minutes in. So, but I just wanted to show you that for personal projects, for example, you want to track both the project and manifest because of reproducibility. For example, if you want to share your study with the rest of the world for publication, you want paper reproducibility. So that's, just now I gave you an example of downloading the manifest, compiling the environment using the manifest example. Yeah. So next one is, why do we have different environments? So basically, there's the question that is being asked in this slide is, why do we have different environments for different projects? And that's also because different projects may have different requirements and therefore may have different package requirements. So, for example, okay, let's do this. Here. So this is another activity to use to show you that different environments are independent of each other. For example, for example, okay, sorry, let's see. Okay, and then after that we do this. We do this, and we do this. So we have two different. So basically, we have two different folders: test project new and test project old. If I go to test project old, and if I install the old version of NASA precipitation, and if I go to so basically I installed an old version of NASA precipitation in this test project old project, and I installed a new one in this test project new here. And then you see that if I use NASA precipitation in the test project new, there are certain features, for example, for example, I can call this function called image_dummy in the new version, but I cannot do it in the old version because the old version doesn't have this particular function, for example. So image_dummy. See, so for example, in this one, in NASA Precipitation, I installed version 0.1 here. In this one, I installed 0.1. I cannot call this function, but when I installed it, I installed the new version inside a separate folder. I can call it, for example. So the versions are. So when you are loading packages, it is important to first activate the correct environment that you are in. So if you're in a particular project folder, you want to activate the environment for that project first before loading your packages. Yeah. So that's just one thing about different environments. Yeah, different environments. So you can compare and contrast NASA Precipitation.jl. I'll leave you guys to do this on your own as an exercise. I will upload the slides. I will upload the slides to GitHub later. So different environments means you can load 2 different versions of the same package. You can actually install and in the .julia let's see cd.julia packages NASA Precipitation. Like you see in this case, in this NASA Precipitation, so basically in this location, this is where the NASA Precipitation packages are installed. You see that there are 3 different versions of NASA Precipitation being installed because there are several different environments on my computer, and each of these environments uses a different version, and some of these environments use different versions of NASA Precipitation. So because they use different versions of NASA Precipitation, there are 3 different versions of NASA Precipitation installed on my computer. But the version of NASA Precipitation that you are using will depend on the project environment that you have activated, for example. So that's about different environments. Okay. So a note that packages that you have already loaded will remain loaded as is. So if you have already loaded an old version of NASA Precipitation, for example, if you have already loaded an old version of NASA Precipitation, for example, over here, this is test project old, and then you want to activate the test project new, and then you want to try using NASA Precipitation, and then you try image_dummy, it doesn't work because you have already preloaded an old version of the package. You cannot override a package that you have already loaded with a newer version of the package. So if you want to load the newer version of the package, you have to exit and enter. Julia again. See, and it works now. So you have to go out. You have to exit Julia and enter Julia again if you want to. If you want to what the hell? If you want to if you want to load the correct version of a package that you have loaded wrongly, you have to exit and enter again. Yeah. So this is a warning. Yeah. Packages you have already loaded will remain loaded as is. So 5 minutes break because this is probably a lot, and I just want you guys to settle down a bit first before we go on into the next section again. Does anyone have any questions also, by the way? Anyone not following? Everyone doing okay? Yeah. Yes.
What was Dr. Watson again?
So Dr. Watson is basically meant to create projects. So it's basically the project version of package template. So package template creates packages, and Dr. Watson creates projects. And then Dr. Watson will create, when you create projects, it will also commit the manifest. And then depending on whether you want to commit the manifest or not, if it's not the final version of the project, then you can go and fiddle around with what is being committed and not being committed. But like, that's just something to know, yeah. Yes?
So the manifest is something like specific to my system?
The manifest...
If I create a package, a project using my system creates a manifest, and I have a Mac.
Mm-hmm.
Someone tries to run my project on a Windows using the same manifest, does it break? Is it something like that?
It should work. It should work. The manifest more is to specify the exact versions of your project that you are, or the exact versions of the packages that you are using. Packages are generally tested for Linux, Mac, and I also think for Windows as well, quite often for Windows as well. And the dependency chain is the same. So,
I think with the caveat of external binaries maybe, right? So if you have an external binary in this manifest, I don't know if it's guaranteed that it will be working. I don't know, depending on how the external binary is actually installed. If it's binary builder and all these things, I think it guarantees it will be
That's true. External binaries do play a role. I know NC datasets also had that problem as well. Like,
The reason for me asking is because I noticed that when I installed a package, some dependencies are compiled on my machine. So that's why I asked. If they are compiled locally here, and someone uses the manifest on another system, it might break something.
it should generally work. Yeah, almost all the time it should work. Like, that's the thing.
Yeah, one of the manifest doesn't share the compilations of the class. So like the manifest just shares like the setup. It's still compiled on a new machine when you use the pre-compile. So it should work. But in rare cases there can be difference. I mean, but I would say most of the packages don't know if it's Windows or it's Mac or it's Linux. And most packages don't care.
Yeah, if something breaks during the compilation, that's more of an issue with the package itself and not so much the problem with the manifest. Yeah.
There's a compilation by Julia that precompiles and caches the result, and that's when you can have errors with dependency conflicts sometimes, and that's independent of the OS. You can get them equally, and there is other type of the binaries when packages depend on external binaries. Those get misfolded. So that installation, there are binaries for each of the three OSs. So they download, that's a different, they were pre-compiled before outside virtual environment. Okay. So unless the errors that they occur keep occurring, it should be completely transparent to any type of OS.
Okay, sorry for the more technical.
Oh, no worries. Like, like these are important things that people should know. That I personally spent like 5 months trying to figure out what the package environment was, or how, like, what exactly the package environment was being used for. So, and especially when it comes to like developing packages, it can be quite tricky. So, just things to.
Pre-compilation, or sometimes it's just a matter of restarting Julia, that you have another version loaded with the package, and then you cannot pre-compile another version. So just restart Julia, and it's nice. So if you see this,
Okay, I guess most of this comes with the experience, right? The more you use it, the more errors you get.
yeah, but if you see a large screen of error, have a look at the really first sentence. Sometimes it tells you I cannot pre-compile this package because I already loaded something. If you see this,
Okay.
close the rest of the RAM, you should just start Julia.
All right. Any other questions? Any other questions? Okay. Okay. So let's get to the next part, which is about actually creating packages in Julia, finally creating packages. So again, we are creating packages using package templates. So usually I use package templates to create and develop new packages. And package templates will automatically create new packages and put them in the development folder in Julia. So for example, if you go into, so basically, where's the development folder? The development folder is in your home directory in the .julia folder inside the dev. And here you will see all the packages that you have committed or that you have committed for development. So if you want to, if you have a package, for example, let's install geotables for real this time. If you want to add geotables, and then after that, if you want to for example, make some changes to geotables on your local computer, and then makey compilation, makey. Faster. Never mind. But if you want to develop a package, usually what happens is that when you press dev geotables, for example, or maybe dev of another package, Julia will automatically create a copy in the development folder. It's taking a while to load, taking a while to compile, but that's makey for you. Sorry, Simon. Compile. Okay, so I already have geotables installed. So let's dev geotables. And then if you go back to your dev folder, you see that in dev, you will have geotables as a package that you are developing. So when package templates, when you're creating new packages using package templates, it will also automatically put whatever new packages whatever folders you have into this particular folder, so all the packages that you are developing are in this particular folder. So for bookkeeping purposes, yes, for bookkeeping purposes. So this is the development folder where all the packages you develop are stored, and you can also develop pre-existing packages. So all you need to do is you need to do this. You need to do the square bracket, then dev develop whatever package name you want. So that's how you develop. That's how you put a pre-existing package into the development folder. And now it's your turn. So try developing. So if you guys haven't, this is you guys trying to develop your first package. So the first step, of course, is to let's go back to the main. Is to add package templates, because package templates again is not automatically installed on Julia. I already have it installed on my local machine, but if you guys want to use package templates, you have to go and add package templates. So if you guys haven't done that already, you guys should do that. Add package templates. Shouldn't take too long. And then using package templates. And the first thing and then the thing that you should note is that, and then what you should note is that package templates exports this function called template here. And then what you want to do is you want to do something equals to template. So A equals to template, for example. Because it's the Git problem. Let's see. This is the Git problem. I'm not sure if any of you guys also have this same problem that I have, which is that I need to specify that the user so user netgeo Wong. Let's try this again. So I can do A equals to template A with template this particular thing is a function. This is a function, so template whatever is a function. A is whatever you're storing it in, and then you do A my new package. And then what package template does is that package templates will automatically activate a new project in the development and will automatically create a new folder in the development folder, and then after that will activate the project there, and then it will do all sorts of stuff in your new in the package called my new package. So now see here, if I do status for my main environment, here, no, it's not here. It's not here. Okay, never mind. But if you go to .julia dev, you should see that I have my new package in this development folder, and this is where your new package. This is where you go to develop your new package. So if you go to VS Code, let's just open that folder, the my new package folder. What do you have in this new package? So yes, I trust the authors. So in this so what basically happens is that when you use package template to install or to develop a new package, package templates already has a set list of stuff that it will automatically put into this folder. Basically, you have your project. You have your project .toml. Yes. Oh, sorry. Okay, so what you have to do is you have to do A equals to template. This part here is because I think somehow from a computer I needed to get. That's your GitHub username. Like this is my GitHub username, but I don't know if you need this. I don't know if everybody needs this. Technically, you shouldn't, but for my computer, somehow you need this. So I don't know why. But all you need to do is A equals to template, and I think you can just be an empty brackets. And then what you need after that is A bracket my new package, or bracket whatever your package name, whatever you want your package name to be. So when you do A bracket whatever you want your package name to be, it will create that package in the dev folder. Yeah. Does that make sense? Yeah. Everybody got to this step? Anyone who hasn't gotten to this step yet? The creation of a folder in the creation of a package yet? Anyone hasn't gotten to this step yet? Okay, so now we have this. So this is what is inside your new folder. I'm using VS Code to show you guys. Okay, so basically it will commit. It will not commit. It will create a project. It will create a manifest. It will then also have a README, and the README is basically when you upload to the GitHub. The README is basically the front page, and then the important part, the part where you guys want to create functions, to create stuff in, lies in the folder called source inside my new package, and then my new package, if your package name is my new package, inside source, the main Julia folder is my new package.jl. So if your package name is random package, then in the source folder, the main file is random package.jl. So in my new package.jl. Here is where you will write your functions. Here is where you will export your functions so that other people can use these functions. Here is where you will want to say, I am using a certain package. So I'm, for example, using dates. So dates, like to specify a date and a time. For example, I will be using dates. So this is an empty package, so there is nothing inside here because you guys have to write whatever code or whatever functions you want in this package and then export it for it to be usable. But now I want to show you guys an example using georegions.jl, I think that's the next one. Yeah, so the thing is, so now the question is, what does a fully formed package look like? So this is, okay, let me close this, close others, close this. Okay, so let's also close everything else. Everything else is not important. Okay, so basically, georegions.jl is, I'm going to use georegions.jl as an example of a package that is more or less fully developed or more or less in the mature stage of development. So just now, for example, you had my new package. Inside here, you have module, my new package. You write your package code here, you have N. So module, georegions, you have everything going on inside the main, and then you end. So for example, so everything that you want to do, every functionality that you want to create for your package from A to Z must go within the main, must be at least specified within the main, let's close this, specified within the main Julia file, which is georegions.jl in this case. And you notice that in the source, I have other Julia folders, I have other Julia files. It's because they are all included below here. So if I write functions in other files that I want to be called, I have to include the functions, I have to include the files in the main georegions.jl file. So this is an example of what a fully formed package looks like. And don't worry, I'm going to go through everything step by step. So this is what a package looks like. Okay, so basically a package, you will have your GitHub workflow. So a GitHub workflow is basically like for testing, etc., to ensure compatibility. You have your documentation, where if you write documentation so that people can understand what your package is doing. And then after that, you have your source, which is basically where you have all your Julia files and your Julia functions that you will write. And then you will export those functions elsewhere. And then you have tests. I don't do tests, which is not a good thing. Like, it's not a good thing, it's very bad practice, but I don't do tests because I learned everything on my own. So I never learned how to do tests, so I've always avoided doing tests. But you should not avoid doing tests. I know I know it's very bad. I'm setting a very bad example, but you should learn how to use tests where you can. Yeah, and then you have the project and the manifest and the README, for example. So that's what a project looks like. That's what a project folder looks like. This is what. So basically, this is what a module looks like. So basically, in a module, you will use packages, your dependencies. So for example, in georegions.jl, I have all these dependencies. I have dates, delimited files, geometry basics. I will call all of them here in modules used. So here you will see, you see that in the modules used, using XXX, which is basically using whatever dependencies that you have. So dates, delimited files, everything here. Import is basically if you want to import a function. So in base, you have the function called show. If you want to re-export a function, if you want to re-export show and read, you have to import it from base and then later you export it. And then this part here, export. Export is where you will list all the functions that you have previously defined to be exported. So for example, in georegions.jl, I am exporting this thing called georegion, region grid, abstract landscape. I have defined these later on in the package, but in order for other people to use this functionality, I need to export this functionality. No function, so if you want to use georegions, and then after that you want to use the function in georegions called reset georegions, for example, I must export the function reset georegions so that other people can use reset georegions. Does that make sense? Yeah, okay. So that's exporting the functions, and then you also define this thing called types. We will talk about types later, what types are exactly, and how you can use types in, why types are important in package and multiple dispatch. We'll talk about it later. And then after that, you include other files, you define your functions, and then you include other files in the module and other files with functions, for example, in the module. And then it will, one thing to note, the order here, the order in which you do this does not really matter. So you can scramble your, so with one exception, but I'll give you the exception later. But in general, if all these are just functions, if all these files just contain functions, you can scramble the order in which you include them anywhere. Doesn't have to be in sequential order. Yes.
And if there is a using in one of the functions, so is also loading this dependency when you are doing include?
Using, you mean inside a function, then you say using.
For example, I construct the field, you include your file that contains the function.
Yes.
And if in this file there is a using to load a certain package, a certain package is also loading.
It should load. From my understanding is that it should load, but best practice is always, if you need something inside here, you should always put it out here as well. Just you know, like it's a dependency thing. If everything in your dependency should, if you're using it, you should put it out here. Like just for like, because sometimes, because a lot of, when you get more familiar with Julia, quite often what you want to do is you want to go, when you want to get a first glance of what dependencies are needed in the package, especially when you're trying to fiddle around with clashing dependencies, what you usually want to do is you want to go to one file that will show you all the packages that are loaded in this particular, all the dependencies that are loaded in this particular package. So if all the dependencies, you should put everything in your master file. You should put everything in the main module file, which is, in this case, georegions.jl, because the package is called georegions. Okay, so that's what a fully formed package looks like. So I want to step back a bit from when talking about what a package looks like, and I want to ask people, like, the thing, I want to step a bit more into the philosophy. I have half an hour, should be enough. I have half an hour, so what people are trying to accomplish when you are designing a package. So when you want to design a package, especially for Earth observations, what are you going to create a package for example? Like, does anyone want to share what they would want to create a package for in Earth observation if you guys haven't created already? Like, yes.
So I would say there's three main reasons for why I create packages. The first one, I want to create something, some kind of tool that, show you some microphone. Some kind of tool that I really want others to be able to use as well. Most of them, they're rather small because I don't necessarily have the time to learn something really, really big. And to make sure that it also is available to, really well maintained for others. But it's really something that I want others to use, and most of the time that's something like rather independent that other people can somehow integrate into their workflows. The second reason, I think, is basically a documentation for myself. So that I, for example, say like, I've worked on this research project, and I basically throw all the scripts, all the notebooks that I've written for it in there, sometimes even with the figures, sometimes even with like including PDFs and so on, so that at some point later I'm just like, oh yeah, I worked on this research project, I can just go back to that. And either this is really just for myself and I don't bother about making it somehow like documented so well so that also others can immediately use it, or, and this is the third reason, I really try to create a package so that with like an instruction so that others know what I've done and how they can recreate that. So for example, if you think about like some kind of simulation that you run, and you may have a certain setup in order to create an, I don't know, an ocean and atmosphere in the way you want it to, then you, for example, you could write it all in there, and you could even like turn it into a little package and then say like, using my fancy model setup, and then you can basically have like a couple of commands, and then you can recreate whatever that person did for that project.
So basically for like workflows and for documentation purposes, basically. Is that what
Exactly.
you're
So it's like documentation mostly for myself, documentation for others as well. Also like a tool that is, and the third one, or that I mentioned first, is some kind of like tool that I really want others to be able to use on a like, let's say, frequent basis, and not just in terms of like, what have you done back then once?
Yeah. Yes.
Sorry, I would also say that creating a package is useful when you have some kind of difficulty that you're working on, and then you have some idea to make something that is difficult more easy for me to use and for others to use, and the package might be good for that. So I might have an idea for a new way of downloading large data sets, and I create a package out of that to make it easy with a simpler syntax or a simpler command, so people might download a difficult data set or something like that.
Yes.
Maybe I can start. So I also sometimes create packages, and it's also to be able to like share the code I made and the tools I made with others so they can use it. And I think like before I knew how to make packages, what I would do was I would just send files around and be like, I made this code, maybe you can use that. But creating it as a package also have the dependencies, and it's easier to install. It's set up. You can do different versions, so you can increment the version. So it really takes like sharing the code to another level and make it really the reuse much easier.
Yeah, I mainly make packages for myself, which is, I guess, not what most of the people in here do. But I make them so it's easier for myself to use them for other projects, because a lot of my projects are building on top of each other. So like what you had up there, you had one package you told us to install, and you had 2 versions, and you had other packages that use those versions. That is why I make packages for myself. So I have one project, and I make a package of it, and then I have another project that is using that package. And that's just easier if it's a package. Yeah.
Okay. So all good answers. Most of what I probably am focusing on is more documentation of personal projects, also important, especially when it comes to complicated like models and so on and so forth, like model. But more of what I was thinking of was on streamlining of workflows, like the downloading of data sets, for example, data retrieval, data analysis, plotting and visualization of data, for example, when we are doing. So basically, like from online servers, data repositories, for example, NASA Precipitation, the package that I use is basically data retrieval and a bit of data analysis. And then, so the thing about when we're talking about creating packages for Earth observation is that, like all these, when you're creating packages in Earth observation, most of the time what we're doing, especially when we're talking about streamlining workflows, is because there are actions that you will perform on the data set. So the reason why I'm talking about this is because I find that when we are creating packages, sometimes, depending on how we go about it, sometimes people create packages. Sometimes when people create packages, it's a bit haphazard that we always try to make packages. We try to make packages that can do everything, and sometimes I feel that is good, but sometimes there's also value in keeping things relatively specific or so we can define. So in my case, when I usually create a package, I'm just sharing my philosophy. Like guys don't have to follow it, but this is what I do when I usually define a package. I usually first focus on defining the data sets that I want to tackle with this package, and then there are components. This is also more related to observations. So observations, satellite observations, reanalysis data sets, for example. So it talks about how would I organize a package. So usually when I design a package, this is more for the people who are just starting out designing a package. A lot of us, some of us here in this room already have experience in designing packages the way we want to design packages, or have designed packages, or have a lot of experience in designing packages. A lot of people will come up with their own methods to design packages in a streamlined and in a streamlined and effective way. But for me, the way I design a package is when I design a package, I usually think about three things. I want to talk about what the package is supposed to, what the package is supposed to do, or how the package is supposed to handle the file system, how it's supposed to handle where it puts all the data that I've downloaded or that I have retrieved. I'm thinking about the different components. So in Earth observations, you don't just have the data set that you're looking at, you have the variables in the data set that you're looking at, and you also have, quite often, because it's Earth observation, you're looking at a specific region, you're also interested in the specific geographic region a specific geographic region of interest. These are components in my opinion, these are component parts of the package. And what we're doing when we're doing downloading and analysis and calculation and plotting and all these things, these are actions that we are performing on the components of a package. So for example, when I create a package for ERA 5 reanalysis, for example, let's just look at the example here, right here. So when I have a lot of different folders, and the reason why I have all these different folders is because they all serve different purposes. For example, I have some things like the file system and the land-sea that is a general part of the package, and then after that I also have data set, I have variables, I have a variable and I have region. These I consider to be the package components, or the things that I need to specify in order to retrieve the data that I want, or the things that I need to specify in order to retrieve or download or analyze the data that I want. And then the green parts, which is basically analysis or downloading or from conversion from hour to day, for example. These are all actionables. These are all actionable things. And then of course you have the miscellaneous back-end stuff as well. That's my general philosophy when I create a package, for example. So this generally means that when at least, and I'm especially talking to people who are just newly starting out using Julia, when you want to design a package, you need to think very carefully about what data is available and what data is provided for the data set that you are interested. That you need to be able to go in and explore the data set first before you decide to create a pack, and be comfortable with exploring the data set before you go in and design a package. Just go in and design a package. So before, for example, if you want to retrieve something that's for example, Sentinel data, for example. If you want to retrieve Sentinel data, first you need to know where to retrieve the Sentinel data. You need to know how to retrieve the Sentinel data, like because when you retrieve Sentinel data, often there's like login and stuff. You need to be able to you need to know like the address, for example, what the patterns of the address are, because usually when you save when they save large data sets, there's a certain pattern in which they save the data sets. Then what the package is going to do for you, and you may not want to retrieve everything that is available. So for example, when I'm talking about, when I'm doing NASA precipitation, right, I am retrieving precipitation data. There is also a lot of other information that is available in the Global Precipitation Mission, which is the overarching mission for the precipitation data. So for example, here you see that, let's zoom in a bit. So you see, for example, when you download a HDF or when you download a data set for a single timestamp from GPM, you will find that there's a lot of extra information. For example, there is infrared radar precipitation, there is uncalibrated precipitation, for example. Or this is like, the details not necessarily important, but what I want to say is that when I was doing NASA precipitation, I was only interested in total precipitation. I knew I was only interested in total precipitation. So when I wrote my package, I did not write my package to include all these other variables that most people don't use. Most people don't take into account. Not they don't take into account, but most people just don't use these data sets unless they are in a very specific field. For example, most people are more interested in total precipitation, in the longitude and in the latitude. So when you go into a server and you retrieve a data set, you need to know what exactly you are retrieving and what exactly you are retrieving, basically. So the thing is, do you need all the extra data that is provided here, or do you only need just a few things? Because again, quite often when you're developing these packages, you are only one person and your time is limited. So you need to do what is most cost effective to you, and to the community at large, for example. So if the community at large only generally uses precipitation data and not the other fields that they provide, you don't necessarily need to think about the other variables that are included in this data set, for example. So, and then also you have that packages can also handle multiple data sets, for example. So, for example, there are many, GPM provides, when they provide total precipitation, they don't just provide total precipitation on half-hourly. They also provide it for daily. They also provide it for monthly, which is all specified here. Sometimes you do want your package to be able to handle multiple data sets at once. Not at once, but you want it to be able to handle multiple data sets that are provided, multiple data sets that are similar that are provided. So but the thing is, each of these data sets, for example, when you download half-hourly precipitation versus when you download monthly precipitation, the file convention is different in half-hourly precipitation compared to monthly precipitation, for example. So the data sets have different properties. They each also probably have different performable web actions. For example, if you want to download half-hourly data, you can convert half-hourly into hourly data or 3-hourly data, but you cannot convert daily or monthly data into hourly or 3-hourly data, for example. So certain data sets, so all these data sets will have actions that you can perform on all of them, and some of them have actions that are specific only to some or each of them. So in a single package, how do we handle multiple data sets? Is using types plus multiple dispatch. So this morning when Iga was talking about using types or using structs, for example, this is what we mean by type. So basically, a struct here is basically kind of like an object. It's basically like an object that is, it's basically kind of like an, types are basically like objects, for example. So if you have a certain object and you know that an object is of this type, then you therefore when you say, I'm trying to download this particular object type, I can, when I by specifying a data set as a type, as a struct type, you can then say that when you call a function for a specific type, like using a specific type, that function will perform a specific action. Sorry, I'm not explaining this extremely well, but it's called multiple dispatch. So for example, in georegions, for example, let's do this. For georegions, for example, there are two different types of regions. One is a rectangular region and one is a poly region. So just now there was a rect region strike. So I have two different functions. I have two different functions here. They are the same name. So there's a region grid function, but there are two different methods for this region grid function. One is based on the rect region type, and the other is based on the poly region type. So when you have an object type, when you have a specific object type, you can specify for functions with this. You can specify that a function has two different methods, one for each type. Does that make sense? Does that kind of make sense, what I'm trying to say? Yeah, so if I have, so just now down here you had a rect region and you had a poly region, and they were subsets of the georegion subtype. So because you have a rect region and a poly region subtype, you can have two different methods you can specify two different methods for a function with the same name. Yeah, so that's how you can handle multiple data sets in a package. You specify that a data set is a type, so it's a type of data set, and then using multiple dispatch, you can say download, and then download basically because it is of this type. You have specified that you have created a data set of this type. Then you can download the data set of this type with a specific, and then it will call a specific method to download the data set of this type. Does that make sense? Yeah. So basically, for example, in NASA precipitation, there's iMerge datasets, and then there's trim datasets, and iMerge datasets has half-hourly, daily, and monthly, and trim has 3-hourly, daily, and monthly as well. And then when you do the downloading, for example, you can download every half hour. You can download the half-hourly datasets or the daily datasets or the monthly datasets, for example, but you can still use the same. You can still use the same function name. So it's just download Yeah. So that's one of the benefits of using Julia, for example, multiple dispatch. I'm not sure if Python has an equivalent, but this is one of the reasons why I like using Julia. So I can specify everything with a simple function name, and then I can extend the methods of that function name with using types that I have defined in the package itself. Because all these types that I am talking about here, for example, this abstract type here, abstract georegion, you must define it in the package itself. So you define it in the package, and you define the subtypes in the package itself. And then that's how you extend the methods, and that's how you that's basically one of the reasons, or not one of the reasons, but like when you're doing a package, one of my main recommendations is to use types like that. So if, for example, if you have SAR data, for example, and you have different types of SAR data, you might want to use different types for different types of SAR data. Yeah, pun. Okay, but okay, so that's that, multiple data sets in the package, and I wanted to go through like why I just wanted to go through the thought process, or at least explain the thought process of creating a new package, on creating new packages in Julia. Yeah. So the next thing about package creation is that when you design a package, you are the one that understands the package best, but not everybody understands the package. Like if you ask someone to dig into your code to understand the package, that's not really going to work. So a good Julia package not only is comprehensive and well organized, but also must be easy to understand for different people, which brings me to documentation. So package templates will set up documentation. Will set up the skeleton of the documentation for you. But if you want to know how to use documentation, you should go to Documenter. You should go to documenter.jl here. This is another Julia package for documentation. It will basically set up documentation for you. So basically, this is the documentation for my package. So let's go to, so basically, do I have it? Yeah. So basically, when you create a package, you also sound like a good practice is to create documentation. So when you create documentation, for example, this is the documentation for my GeoRegions package. I have tutorial on what GeoRegions are. How do you use GeoRegions, for example? Like this kind of documentation is also necessary for a good package, for example, especially if you want your package to be widely used or you want other people to be able to use your package easily. Yeah. Okay, so that's documentation. Okay, so TLDR, package templates is a good tool. I showed you, you guys already had, I already made you guys do a short example or a short activity on how to create a package using package templates. And then designing a package requires familiarity with the different data sets and the variables in the data sets. So if you want to design a package, I recommend sketching out what your package is supposed to, like I recommend that you guys do a sketch of what you want your package to do first before you actually start coding up your package. Because speaking from experience, especially from GeoRegions, it's not super straightforward, especially when you're starting out. When you're starting out, there are a lot of best practices that you don't necessarily know. So I recommend sketching out what the data sets and the variables are in your package, what is the same between different data sets and different variables, what is different for different data sets and different variables. Multiple data sets can also be handled in Julia using types and multiple dispatch, and documentation is also necessary. And we have another break, 5 minutes. Does anyone have any questions on what I've presented so far? Any thoughts? Yeah. Yeah, so bit of give people a bit of a break for like 1 or 2 minutes just to come down a bit, because it's a lot. Yeah. Yes.
It's just a quick comment that, like in Julia packages, the documentation is often part of the package, the source code. So it's just something that's edited in the same folder. And also, if you add doc strings to the functions, you can include that automatically, and it also shows up all the right places when people need it. And then I think you clicked really fast on the documentation tag on the GitHub folder. That's a really useful resource for a lot of Julia packages. When you find the GitHub folder, there's the small documentation tag, and if you click on that, most of the time it opens some documentation.
Yeah, I'll be going through GeoRegions.jl as a package, so I will go through a bit more on documentation later as well, on what doc strings actually are and how you put doc strings in the Julia file as well. Yeah. Okay, so I think we won't have time to cover everything because I only have, 20 more minutes? So I will just go through 24, 25. But I don't think people want to stay much past 4 anyway, because we have a reception upstairs later. So I'll just go through this. I technically have a 4th part. This is the 3rd part. This is the 3rd part, which is I'm just going to be using georegions.jl as an example of a package. Like I've introduced several different concepts before. Now I want to bring them. Now I want to show you how I use them in georegions.jl, for example. And then the 4th part, which is on how do you use georegions.jl. That one I'll upload it, and then you can look at the Pluto notebooks, etc., and go through. Or you can look at the documentation. Yeah, you can look at the documentation. But I just wanted to get. I don't want to necessarily rush through this 3rd part here. So the 3rd part is on creating packages in Julia and using GeoRegions as an example of a package that I've created, for example. So basically georegions.jl deals with a bit of background. Georegions.jl basically deals with gridded data. So you specify an ID and a name for a geographic area, and you specify the boundaries or the shape of that region using the different coordinates. And then you can, and then with that particular shape or that particular region along longitude, latitude is what I consider a geographic region, or a georegion for short. The reason why I created this package is specifically because I wanted to be able to specify regions to download data. So if I, for example, wanted to download NASA precipitation data only for a specific region, then I would use GeoRegions to specify that region for downloading, because the NASA precipitation dataset is huge. It is 0.1 degrees by 0.1 degrees, which is 3600 by 1800. And then you have, it's every half hour, and it's 20 years worth of data, and that is terabytes worth of data. And you don't necessarily want, unless you have the storage space and the internet bandwidth, you do not want to download terabytes of data. Which is why when I created georegions.jl is to help me specify small regions so that I can download them faster. Yeah. So, like I said, learning how to use georegions, probably I don't have time for that today because I'm running over time. But this section is focused on using georegions as an example of how to organize and structure a Julia package based on what I was talking about before. So we can go back later and compare against some of the concepts that I mentioned just now with regards to types and methods and multiple dispatch, and to show you guys the thought process between the thought process for georegions.jl, because currently georegions.jl is version 5. And then 1 year ago, it was version 3. And then the thing is, why did I bump it up 2 versions? So basically, the upshot is because Julia follows semantic versioning. So if you publish any of your packages as version 1, if you create breaking changes, and by breaking changes, what I mean by breaking changes is that if your code no longer works when you update your version, that is a breaking change. So if I did download something for version 1, and then the next version was I did the same thing, download, and it broke because I changed the method, or I changed the keyword arguments, for example, the arguments of the input, that is considered a breaking change. Yeah. So one thing that I would advise is that when you're creating a package, you do not try to rush to push towards version 1. You can keep it as version 0. whatever for an infinite length of time. For example, Maki, for example, I think is still version 0.26? Yeah, it's version 0.20 or something like that. So like, and then Oceananigans, which is the is version 0.680 or something like that. So there is no, yes, and yes. Mm-hmm.
Now it changes the old version to 1.00 dash.
Mm-hmm.
So this is maybe also something that people want to adjust.
Yeah.
Not directly start with a version 1.
Yeah, but when you create that, but the thing is, when you create the version in the project version, in the project tomorrow, you can just modify it, versions back to version 0.1.
It's better to start with a 0.1 version.
Yeah.
Starting practice.
Yeah, like, because especially since you generally want to try out your package with the wider community, but you don't want to commit to a version 1. So you usually go to version 0.1 or something like that. And then you can keep it a version 0. Something for the rest of your life if you want. No one's going to force you to push to version 1. I personally think I pushed to version 1 a bit too fast, and that's why it's not a version 5. I don't know, but it is what it is. So if we want to explore georegions.jl as an example, so basically when we're talking about package, component, and actions, there are many different so this part here, there's no real file system handling for the package, so that's not completely relevant, but I wanted to elaborate more on the components of georegions.jl and the actions that I performed using georegions.jl and what I classify as components and as actions. So, for example, components, for example, a georegion is a component. A geographic region is a component. And then from a geographic region, you have a region grid. So from a longitude, latitude grid and a georegion, you can come up with a region grid for that specific georegion. And then there's also abstract Landsea, which is a Landsea data type. And then the thing about all these components is that if you look in georegions.jl, if you look at the source code for georegions.jl, you will see that all these, georegion, region grid, and abstract Landsea, these are all abstract types. So for example, abstract type, georegion is an abstract type, region grid is an abstract type, and then abstract Landsea is a abstract type as well. So all my when I'm talking about components, a lot of the time I'm talking about especially when in georegions.jl, I'm more or less talking about abstract types as well. So for example, if you look at some of my other packages, like for ERA5 reanalysis, for example, you will find that the ERA5 dataset is an abstract type, the ERA5 variable is an abstract type, the ERA5 region is an abstract type, and then all those are components of my ERA5 package, for example. And then there's also actions that I can perform on all these. So for example, I can use the georegion abstract type to say is point X in point Y, or region grid to do data extraction, for example, or I can use the Landsea dataset to download topographic data, for example. So again, the master file of package name is always found in source package name.jl. So this is the starting point of every package. And again, this, for example, in georegions.jl, the master file is in source georegions.jl. And then I do want people to note the order of what I am doing inside the source of georegion.jl. So in the source of georegion.jl, what I did first is that, okay, it's not here, it's here, is that I loaded the package dependencies first here. I loaded the package dependencies, and then I exported the and then after that I exported the package types, package functions and the types. So you can export functions and types as well. And then after that, I defined the types. For example, down here, all the way below, I defined the types. And then after that, I defined the functions. So the one exception to the ordering of your functions, etc., is that you must always define your types before your functions. If you don't define your types before your functions, your package will throw an error, because this is especially true when your functions are using types that you have defined in your package. If you, for example, I used abstract landscape, for example, here. I used abstract landscape inside here, for example. But if I included landscape, this file, on top first before I defined what the abstract landscape was, the package will throw an error. So you must always define your abstract types first, or your types, or the relevant types first, before you use them in functions. Does that make sense? Yeah. So the one thing that you can shift around is the export. So you can shift around this part from here, or you can shift it all the way to the end as well. It doesn't really make much of a difference. And also, but besides the fact that you cannot define functions before types, you can shift around everything. You can shift around all the different the order of the files that you have included here. So the order of the functions in which you define your functions doesn't matter. The only thing is that the types must come before the functions. Yeah. Yeah. So loading package dependencies when you're using something, using a package, it's using the term using is okay for most cases, but when you want to re-export a function, you need to use import base. So if, for example, I'm defining, not re-export a function, sorry. If you want to define a new method for a function that already exists, so for example, in base, base is always loaded. So show and read are functions that are always loaded in your package when you're using Julia. If I want to define a new method for show and for read, I need to use import. So import is when you want to define a new method. You cannot use using. If you want to export the package functions and types, the order of which you export doesn't matter. I usually put the types first for bookkeeping purposes, and then I export the functions. So the first section here is types, and then the second section here is functions. And also exporting types is important if you want to create a parent package that relies on georegions. So for example, in NASA precipitation.jl, I use georegion types. So because I use georegion types in NASA precipitation, I must export the georegion type from the package so that other packages can use it. So let's give an example. So in ERA 5 reanalysis here, I use you will find that in a lot of let's see, I use let's see, sorry. So for example, to create an ERA 5 function, I need to use a georegion. I need to specify what the georegion is. So because I'm using a georegion, the georegion type, I must export the georegion type from georegions.jl. It's the same as exporting a function basically. So if you want to use a type in the parent function, you need to export it in your subfunction as well. So yeah, so exporting types is important, and the type must be defined before it can be used in a function. So for example, in the master file, I defined abstract type georegion first, and then only after that I could use the rect region and polyregion types. The next one is that to define your functions, the order of the functions don't matter, but I need to remind you again that the types must be defined first. So for example, So for example, when you're talking about the order, the function doesn't matter. So this function, so for example, the polyregion function, there's a function called polyregion and there's a type called polyregion. But the function for polyregion was called first, but was only defined later in the package, for example. So the order in which you define your functions doesn't matter. The package automatically knows that it's a, the package automatically knows, will automatically be able to tell, will automatically be able to cross-reference different functions in different files, regardless of the order. Yeah. So that's GeoRegions as an example of a Julia package. The thing about why I want to talk about all this is because I learned all these practices by trial and error, so I committed to version 1 a bit too early. So, for example, version 1 to version 2, for example, version 1 was really basic. It was just basically, I was just basically using strings. I was basically using strings to define, or I was just basically using strings and not types. So it became very hard to well, it's not hard, but it became very messy. The package became very messy until I shifted to using types to redefine all the methods and all the functions, etc., etc. So that was like version 1 to version 2, and that was so in version 2, because I had types, I could store and save information about the GeoRegion without having to keep calling functions over and over and over again. So in version 1, for example, if I wanted to know the name of the GeoRegion, I would have a function name called GeoRegion name. But now all I need to do is I would just load the GeoRegion. I would just define the GeoRegion to be the GeoRegion, and then after that I will have the GeoRegion geo.name. I would just keep calling geo.name instead of having to call the function to read the files over and over and over again to find out what the information was. Because the information, because now I'm using types, is already saved in an object that I have called in Julia, because I'm using types right now. And then the reason why the reason why it jumped several different version packages is because I kept changing field names, the names of the struct fields. So for example, when we look back and we see, where is it? Here. So here we see that in type, you have the fields. So ID, PID, name, all these are fields. This is what I call fields. What I did is that from version 3 to version 4 and version 4 to version 5, the field names started changing. So because the field names started changing, the field names changed a lot. It was a breaking change for several different, packages, breaking change basically. So I had to bump up the versions again. So basically in the sense that when we're talking about field names, a lot of the times when we're talking about making packages easy for people to use, we want for example, the field names to be as intuitive as possible. So for example, the ID of something, if you have a field that is the ID of a GeoRegion, for example, the identification, you just call it ID. Like in my first iteration, I call it REG ID, which is like region ID, but I found that it was it was not intuitive, for example. So when you create packages, for example, a lot of the times when you're doing these kind of things, I just want to remind people that simpler is always better. Things that are more intuitive are always better. That kind of, I just want, like, these are things that you need to take note of when you're designing a package, especially when you're designing a package for public use, because it can be quite we can get a bit carried away, I feel like, or at least I get carried away, and also because I know the package best, but that doesn't mean that other people know the package as in-depth as I do. So a lot of these things you need to I'm just trying to remind people that you need to consider these things when we are creating Julia packages. Yeah, and then, okay, now we're talking about this part. We're talking about doc strings. So just now there was mention of documentation and doc strings. So what exactly is a doc string? A doc string is basically something, in Julia, a doc string is basically a documentation string that you put on top of the function itself. So that's how when you do documentation, documenter.jl, which is the package, documenter will automatically translate all these strings into your documentation online. So for example, the doc string here, let's zoom in. This is the doc string here, @georegions for @georegions here. With this doc string here, it automatically translates in documenter.jl will automatically translate this doc string into something into a HTML format like this online over here. So when you're creating a package, it is always generally advisable to put doc strings on top of your functions, so that when you do documentation, it comes out from one to one, basically. So this is an example of a doc string and documentation in Julia, and how we do documentation in Julia when we are creating functions and packages at the same time. And then you can export functions for use in other packages. So for example, georegions.jl exports the Lancy type, so Lancy flat type. So here is the Lancy flat. And then NASA precipitation. This is the module for NASA precipitation. When you're doing, it uses georegions. It uses this type. So NASA precipitation has a Lancy type that is a subset of Lancy flat, which is basically from the georegions package. So that's how. So when you export, so basically using this is example of how you can export a type that is later used in a parent package. So basically, with georegions.jl as a dependency of NASA precipitation.jl, georegions.jl exports a type that is used by NASA precipitation.jl, for example. Yeah. So okay. So that's how you do it, and we are at 4:10, and I do not have time to talk about show you guys how to use georegions.jl, but I hope that you guys at least learn something, or at least some things were learned during this long 2-hour lecture. But yeah, thanks for bearing with me, and I will stop here for today. Yeah, thank you. Any questions, comments, anything? Yes.
So in the breaking change, so if you do not document concerning the field names and the breaking change that you mentioned, so if you do not document the field names, then the name of the fields are just internal, so you can change them without needing to declare as a breaking change. And another thing,
because those field names are often used in other scripts, for example. So those scripts are, so for example, when I updated georegions.2 from version 3 to version 4, and then from version 4 to version 5, I needed to go and change a lot of my other packages as well because of that breaking change. This is why I thought it was a breaking change.
yeah. Yeah, yeah. For you, it was breaking, so yeah, it was probably indeed a breaking change. So, and so a way to access the data in a struct is often making with simple functions. So then you can support the old name and the new name at the same time. So that's a way to maintain the API. Another really nice thing in Julia is that you have the get property function that you can overload. So even if you change the name of a field, you can still have it accessible using the old name by overloading get property. So that's also a way to maintain the old names and the new names at the same time. So,
thank you.
My question is about your package that downloads the data. Do you save it in a particular place on the disk that you can retrieve it later, or on the current directory?
So it depends on the data set. For georegions, because I'm downloading eTopo data, I I either just load it on the spot, so I don't actually save the data, but it's in the memory. It's in the Julia memory. So it's something that every time I open the script will just download again. The script will just open and retrieve the data from online, but it won't actually save anywhere on the computer. But you can also specify, but for me, I have the option to either specify to either save or not to save. Does that make sense?
Yeah.
Yeah, I mean, there's an option for it to do
Because
that.
there are packages that do different, that save it on a cache, you download once, and then you save it. And when you save it, you have to save it in particular places. And I was curious about an organization, if you had that option.
I mean, the organization, I feel like, how do I say it? Like, georegions.jl is meant to help with that organization in the sense that it's meant to, it's like you can use the ID, for example, to help specify a file path or a folder path. But all in all, when you create a package, my philosophy is that everybody has their own way of saving data. So there's no real fixed way to do it there's no real standardized way across Julia, for example. I do it in a certain way for my packages. You can do it in a certain way for your packages as well. Does that make sense? I'm not sure if that's answering
I
your
have
question.
another question, but this is a slightly different thing. It's about Windows and in NetCDF.
I have a follow-up on your first one.
Yeah.
So
Maybe, yeah, that's it.
Are you saying that, because you're using Windows?
That's
No,
different. No,
that's a
the
different
next
question.
Oh.
Nathan, just a follow-up and a comment. There are packages that have good practices on how to download and cache. Datadepths.jl is one of them. And there's also artifacts.jl, where you ask to download the first time, and the package will do all the work to check if the data is already on your disk when you call again the same function. So you can check datadepths.jl and artifacts.jl. They have this purpose of, okay, there's a data set. If you download the first time and you place it somewhere where Julia knows how to download later, and then how to load it back later, and then the next time you call the same function, it will look in that directory. It's a standardized like .config folder somewhere, and then it's going to just load from disk. And you have options to configure that as well. So 2 packages that I would say.
I probably need to talk with you about that later.
No, let's chat. There's 2 ones. I think there are many more, like at datadepths.jl and artifacts.jl. I think these are 2 ones that I have out of my head. Probably using some of this as well, like disk arrays or something. Yeah. Exactly. Yeah.
But my other question was about curiosity. If you download a NetCDF file, the file is big, and you only want to download a little bit, how do you do that? I'm giving off the answer. On Linux, GDAL is able to download a subset, but this is with the trick for Linux. That trick does not work for neither Windows nor Mac. So my curiosity, if you have a big NetCDF file, you don't want to download it all. That's more common than the opposite. How do you manage to download just the bit that you are interested on?
I've been lucky so far. Most of the stuff that I download is from the OpenDARP servers. OpenDARP is you are able to specify exactly, what indices you want, what are the range of indices you want your data from. So using georegions.jl, what I usually do is I usually am able to come up with the indices of those regions and then specify those exact indices that I want to download. I'm not too sure if it's possible to do it for any data set outside the OpenDARP servers, but someone might have a trick for that. Yeah, does that make sense?
Yes, I was more or less guessing that you were going to OpenDARP, which
Yeah.
I know for many years, but not using. Yeah.
But using OpenDARP works on Mac as well at the very least. I think it should also work on Windows.
There's another way in NetCDF library with HTTP ranges. So this does not require OpenDARP server, but it does not work for any dimension. So it depends how the data is stored on the disk.
Anyway, I'm curious. We can talk about that
Yeah.
more. Yeah. Okay. I'm done. Thank you.
Any questions? No, just. Okay. Thank you, Nathaniel.
Okay.
Thank you very much. For those who are online, thank you for staying with us today. We'll be back tomorrow at 9. For those who are here in the room, we have now 1 hour for experts, expert connections, expert hour, okay? So feel free to stay here, to go upstairs, okay? Thank you very much, and see you tomorrow.